is Keno Fischer. I'm CTO for developer tools at Julia Computing, which is a company that we formed to put some more concentrated resources behind the development of Julia. I'm joined by my colleague Bart from the Royal Military Academy in Belgium, and he's going to give you an introduction to Julia as well as talk about his package, CxxWrap.jl, which is one of the two ways to interface Julia with C++. Afterwards, I'll talk about my package that I wrote a while back, Cxx.jl, which is the other way to interface Julia with C++. But before we do that, I figured I would just spend a couple of minutes sort of, catching you up on what's been happening in Julia land, over the past 2 or 3 years or so, and just to give you a sense of what the Julia project is and what the Julia community is, because I always find that important for context. So I just put some arbitrary numbers on the slide. The graph in the middle is just a stupid benchmark slide that we've showed forever, but I'm not going to talk too much about it. The benchmarks are not particularly interesting. But the point is, Julia is sort of in the same performance category as C or C++, is the point. In terms of the Julia ecosystem, a lot has happened over the past, just a couple of years. If you knew Julia in 2014 or 2015, where we had 200 or 300 packages, that has really exploded over the past 3 years, and we're at almost 2,000 packages now. Maintain, and the number keeps growing. It's amazing the kind of things that are happening in the community. And similarly, if you look at other metrics of growth like stars on GitHub, up and to the right. One thing I wanted to spend slightly more time on is this slide, which is that I mentioned there's all these packages in the Julia ecosystem, and a lot of the very good work done is organized around organizations. So these are organizations both in the GitHub sense of a collection of repositories, but also organizations in the social sense of people coming together in very specific areas to write very, very advanced software in various disciplines. And some of these have sort of become industry standards. In particular, I wanted to highlight Julia Opt and Julia DPQ for mathematical optimization, as well as sort of probably the world's most extensive suite of differential equation solvers. And there's about 35 of them which are formally organized, as well as the other hundreds of packages just by individual people or companies. But I just wanted to give you a sort of idea of focus areas that people in the community have rallied around, and these are just 6 of the 35 formally organized Julia organizations. We have a conference. Last year it was in Berkeley. We had 300 people. It's usually 5 days, 150 talks. Next year it'll be in London, or this year I guess it'll be in London in August, which should be a lot of fun. And there was a question earlier of what Julia is used for, and on the Julia Computing website we have a bunch of case studies in industry and academia that customers and partners and friends are using Julia for, and I just took a screenshot of the first couple, but there's about 10 more. So I hope this just gives the very rough context for what Julia is, and if there's questions, ask them later. But with that, I want to hand it over to Bart, who, as I mentioned, is going to give you an introduction to Julia, a technical introduction to Julia, as well as talk about his package, and I'll be back in about 40 minutes to talk about my package, Cxx.jl.
Okay, thank you. So the first thing I'm going to show is the Jupyter notebook that I will use for my slides also. So who here has used Jupyter before? Okay, about a bit less than half, let's say. So the notebook here I wanted to show is from my course material at the Royal Military Academy. So it's about ship stability. And so basically you have a set of cells where you can enter code. It can be a great many languages, even C++ nowadays, but here we use Julia, of course. So using some packages. And then the nice thing is that you can use a manipulate macro in front of a function, for example, and it will generate user interface elements. And so here, for example, I show on a simple rectangular approximation of a ship how the important points change if you change the angle of heel of the ship. And so you can choose when changing the angle whether you stay in the reference of the ship, and so the waterline will tilt, or you can go to the reference of the ocean, let's say, and you can make the ship itself tilt and see how the points change position. So that's just the general idea about the Jupyter notebooks that I'm using also for my slides. So now to start the actual presentation, I'm going to start off with a short bio, so mainly to show that my experience in C++ is a lot longer than it has been in Julia so far. So like I mentioned, I work at the only federal university in Belgium, which belongs to the defense. In C++, I got started on the K3D project, which has been shown here by the previous maintainer, Tim Shedd, on BoostCon 2007, because he was using Boost Python. And this is a direct link to today, in fact, because based on that, on the way Boost Python works, I developed a CxxWrap package for Julia. And so I also gave a talk previously here using Boost Proto with Eigen for expression templates. So the three main packages I'm active in Julia are CxxWrap itself, which I will be talking about today, QML.jl, which uses CxxWrap to make the QML user interface from the Qt project available to Julia programs, and then Quaternions.jl, which is a large scientific library, which I'm also trying to wrap using CxxWrap.jl. So a short outline, I will start with a general introduction on Julia and why it was developed. Then the general intro about Julia will be from a C++ programmer perspective, so highlighting a bit the differences and the similarities between the two languages. Then we will have the discussion about the two languages. The link to the code repository for this presentation and the slides and so on is also on the schedule on the site. So why or what's the main motivation behind Julia? So the idea is that we can have a language that is both easy to use and yields code at a speed that you would expect from a modern computer. So at the same order of magnitude or at the same level as typical C or C++ code. So why is this important for me personally? It's because my students, when I have a research code in C++, it's very difficult to get them to work on that. You have to have real, let's say it kindly, hobbyists that do additional programming in their spare time. And then you might find someone every 2 to 3 years, let's say. But it would be much nicer if you had a simple language that would still result in research code that runs at an acceptable speed on a compute cluster, for example. So that's the promise that Julia makes, and after verifying that it really does that, I started working with it. So then, what is Julia exactly? So it's a high-level programming language that's initially being developed for scientific computing, although it's powerful enough for any, let's say, regular programming tasks. It's a dynamic language, so it's a bit, it's like Python in that respect, that you can just launch the interpreter and start typing code. Unlike Python, it's strongly typed, so everything has a typed link to it, although if you compare to C++, it's mostly like if you type auto everywhere, so you don't have to bother with the types if you don't want to. And everything is just in time compiled using the LLVM compiler. There's a native interface to C, and the central concept of the language is that we can have dynamic multiple dispatch, so that the functions to call are chosen at runtime, or if possible at compile time, based on all the arguments that are passed to the function. So let's start off with a brief introduction. So to define a function in Julia, the code is like this with the function keyword and a familiar return statement. Or for such a short one-line function, you can easily shorten this using add AB. Is it readable for everyone, or is it a bit too small? So these are both equivalent ways to declare and implement a function. And then, of course, if we run that, we get the unsurprising results. And note that we can run it for integers or for floating points, and the same function just works. So the Julia is a strongly typed language, but here we didn't see any types yet. So it depends a bit here on the literal that you type. If we type an integer, by default on a 64-bit machine will be an int64, so it has a strong typed link to it. The same with the result of the addition. And if we go to floats, there are promotion rules. So here if we add an integer and a float, it will give a float as a result. So let's look at the assembly of both of these functions. So Julia has a very nice macro, add code native, that will, when you put the function call behind it, it will print out the assembly code that you get. So for both of our versions, we see that it generates different assembly based on the fact if we are adding integers or adding floating points. So I don't really understand assembly, but I think that this line here, and here it says add, so I suppose that's the line that adds the two numbers together. And so you see on the fly, the first time you invoke a function for a certain combination of types, the LLVM will be invoked to generate the proper version of the code. So let's compare that with C++. In fact, the function we defined so far in C++, if you would want to get the same behavior in C++, you could define a templated function like this. So here it's also valid for any A and B, and you get basically the same behavior as you do in Julia, except that I think the Julia syntax is slightly lighter in this case. Then let's take a look at how we can define a type. So the basic keyword to define a type is struct, and then we can just add the fields followed by 2 colons to indicate the type of each field. You don't have to put a type, so if you want to write a quick prototype, you can just write the name of the field, and it will be of type any, which is the base class of any type in Julia. But then you will get more dispatching at runtime, and it will impact performance negatively. So if you know the type, it's best to put it. In the case of a struct definition anyway. So we can automatically we get a constructor that takes all the fields if we don't define any constructor by ourselves. So the add function that we had previously, obviously it will not work on mynum because the base Julia language doesn't know how to add this user-defined type. So we can create an overload for the add function here. And now we see that it says that add is now a generic function with 2 methods. So basically if we define the function of which the name exists already, with a different typing on the arguments, we add a method. And we can get for every function a list of the methods. So now we have the one we defined first, and then the one including the my number. And so then it works as you would expect. And because we define it to return a my number, it returns a my number. Julia also supports inheritance. So unlike C++, here we have single inheritance, and you have to inherit from abstract types. So you cannot inherit from a concrete type. Small examples, we have a base type called myBase, which is declared using this syntax. And then we can add a concrete type with the less than colon operator, let's say, is set to derive from my base. Julia comes with introspection tools, so you can then use supertype on the name of the type to get back the concrete type. And you can use that also in, when you want to declare a type of something, you can put colon, colon, supertype, and so on. That works. We can define a function on that using the base class as the type, so it will work on anything that is derived from my base. It just gets the field value here, and so if we create one of these concrete types and get the value, it returns the value as expected. Then let's talk a bit about constness, or as it's called in the Julia world, mutability. So when you try to modify the field of the type you just created, you will get an error, because if you just put struct as the declaration of the type, it will be immutable or const by default. It's as if you defined a struct in C++ where all the fields have const in front of them. And so to reiterate, you should put const int and not int const, right? I think there's a discussion going on here about that. Okay, so how do we make a mutable type then? Because that's possible also. Then we just put mutable in front of the struct keyword, and then for the rest I left the implementation of the type the same. If we create that one, we can change the value of the field, and because our getA function just accessed the A field of the object it is passed, this function still works. So that's an important point, because it might seem that not having concrete inheritance is overly restrictive, but it is only restrictive on the fields you define inside of your struct. So if you have defined a base method that uses the same field names as in all the derived types, you don't have to redefine the methods themselves. Yeah.
You have member functions or methods, or are all methods free functions?
All methods are free functions in Julia. Yeah, you cannot. Yeah,
okay.
You cannot have except for the constructor. The constructor you define inside the type, but yeah.
You might answer this question later, so I apologize if I'm jumping ahead. But if you have shared mutable data, is there something like a borrow checker? I don't know if you're familiar with Rust, where you pass it to some other method, and if it's mutable to different places, it won't work. Is there something like that in Julia, or is it just, if it's mutable, it's just mutable?
Not currently. There's some thinking on how to do that in the Julia sort of mindset. On the one hand, Julia is sort of the extreme opposite of that approach, because we don't want to enforce anything at compile time, and the only problem you might get would be performance issues at runtime. So sort of the strict borrow checking in the compiler doesn't really work for us, but there might be other approaches where there can be annotations that the compiler can rely on, and if it can prove the borrow invariance, then it'll generate fast code, and otherwise it'll generate dynamic checks or something of that extent. So there's some thoughts on that, but currently that is not the problem it's addressing.
Okay, thank you.
So then about generic types. So Julia has what in C++ are template types, except we use curly braces and not less than, greater than. So here is a small example using a tuple to encapsulate a point. Yeah, I think it speaks a bit for itself. So you have the type of each of the coordinates, and you have the number of dimensions that you want to put. So you can then you get a default constructor, and so if I put a tuple here, which is just between braces the list of numbers, we get something of the type int64 as the type of the coordinates, and of dimension 3, of course, in this case. So if I pass different parameters, I get a different type. And a bit of a difference for now with C++ is that in C++ you could take two non-type parameters and then combine them to create a new type that does arithmetic on those non-type parameters. But right now in Julia this is not yet possible, although it will probably be in the future. So then about the multiple dispatch. So basically the multiple dispatch in Julia means that it will look up the function based on all of the arguments you passed it, and it can, at the basis it happens dynamically, but if the compiler can figure it out at compile time, it will be done at compile time. So then you avoid the lookup in the tables and so on. That would need to be done in the dynamic case. So I'll just skip to the example. Let's say we have a heterogeneous array. So here I put an integer, a float, and an array inside an array. So of course the element type of the array will be any, because there is no common base that is more specific than that to any of these elements. We can then call the norm function on each element of the array. There is a short syntax for that by adding a dot after the function name, which is called broadcasting. I don't have time to go into it, but it's a very powerful feature of Julia. And so we then get the norm of each of the elements, and there it's figured out that the common base type for all of these was the abstract number type real. So that's what we get as a result. So then, because every element has a different type, it has to dynamically dispatch for the norm. So in C++, how would you solve this problem? If you had a container of different things and you had to call a norm function of every one of them. Excuse me?
You call common type?
Yeah, you may create a common base type and then you have a virtual function called norm, and then it's basically the same thing at runtime. It will dispatch and call the correct norm function for every element. Okay, so that's perfectly doable in both languages. So now let's add a second array, also of type any, with types that don't necessarily have a common base class in common with the first container. And then let's add the elements of these two containers together. So in Julia, what happens here, because both of the arrays are of an element type that's not defined at compile time, it will, for every combination of the two elements of the container, look up the correct plus function defined on the types of the left element and the right element. And so this is, let's say, an important difference with C++, because in C++ you only have the, let's say, the first argument to the function, which you put before the dot in C++, on which it can dispatch dynamically.
Can you say a few words about how virtual function calls, including in presence of multiple virtual arguments, are implemented? Is it using vectors and integer indices or hash maps? Or
I'm afraid I can't say anything on that.
It's very complicated, actually. So I should probably use the microphone. So the question was, how is this implemented? And the first thing I want to say about that is that the only reason we're fast is because the compiler is very good at basically what you would call devirtualization in the C++ world, which is, at compile time when it does specialization, looking up which method gets called and then doing all the standard interprocedural analysis. Obviously, it can't do that forever. It can't do that in all cases. So in those cases, it needs to do the dynamic dispatch. The way that is implemented, conceptually, we have a partial order of specificity, and according to which we can sort the methods. And then what it conceptually does is it goes through and picks the first signature that matches in specificity order. This is too slow for most cases, so there's various levels of caching for simple signatures and anything else that there's call site caches for repeatedly visited call sites.
So it is not as fast as virtual functions.
Yeah, but we don't. But the point is that we don't actually do virtual dispatch most of the time. Mm-hmm. It's very rare in a performance-sensitive function to have virtual dispatch.
Okay.
And it is still pretty fast. It's, you know, if it's cached properly in the last level cache, it's, you know, within a factor of 2 of virtual functions.
But it is not constant time.
No.
Okay.
Just want to add one small thing, is that there's a macro in Julia called @code_warn_type, which will show you in red the places where you risk having dynamic dispatch. So you can optimize those away if the code allows it, or if you made an error where there shouldn't be any dynamic dispatch, but it happens anyway. Okay, so then a short summary table where I just wanted to highlight the differences. So for inheritance, we have single and abstract inheritance, while C++ of course has multiple and concrete inheritance. Though I think multiple inheritance might happen in the future, right? Has been discussed a bit, but I'm hoping for it.
In some way, it will probably not look like standard multiple inheritance.
Yeah. The constants then is at the type level in Julia and at the variable level for C++. All functions are free in Julia. We have both templates. So the difference I spoke about with the computed field types, that may happen in the future. We have introspection in Julia, which I think is very nice. And in fact, in the development of CxxWrap, not having it in C++ was a bit of a headache at times. The difference between the dispatching was already explained at length.
Single dispatch, you just demonstrated it. Single dispatch is
Yeah, it's part of the
It's a special case.
Yeah.
It's not a separate dispatch system.
Yeah.
Right? C++ has 2 dispatch systems, one for multiple dispatch in the static case, and for single dispatch through virtual functions. And Julia is just a special case.
And then the last one I wanted to add, because apparently it's still a point of discussion for C++, but we can overload dot. Is comma an operator? No.
one.
Okay, so now I'll go quickly over the CxxWrap.jl package. So basically it's boost.python, but then for Julia. So it's for the people who already have Python wrappers written in Boost Python of their C++ code. Transitioning to Julia based on that would be very easy. Also, it's for people who prefer writing their code in C++ rather than Julia. So that's the main difference with the Cxx.jl package that will be discussed afterwards. So first, the preliminaries are there's already a native C interface in Julia, so you can use the C call function with then either a symbol name that's already loaded into memory, or the name of the library and the symbol name, or a pointer to a function as the first argument, and then you pass the types, or the return type, the types of the arguments, and then the arguments themselves. So for example, here the absolute value function from the C standard library. We can show that the overhead is quite low. So benchmark tools is a package that does micro benchmarking in a very nice way. So we can just benchmark this. It says almost 4 nanoseconds, and then the native Julia version takes about 2.5 nanoseconds. So for such a small function, we see that even though there is some overhead, it's not up to the point where this will be prohibitively expensive if the function does real work. In fact, if it's a really big function, then the overhead will be completely unnoticeable. So what is the basic approach on CxxWrap? It's that we will generate pointers to functions that can be called directly using C-call, automatically using a syntax similar to Boost Python. So let's dive in straight to an example, a hello world example. So I want to call here the hello function. And similar to Boost Python and PyBind 11, we just start with a macro that starts and ends our module. We create, here the create module function will create a Julia module, which is a kind of package or a kind of namespace, you can think of it in C++ terminology. And then we can just add methods to this. So here the hello method directly by the pointer to the function, or We can also add a lambda, for example, that does the same thing. Then to compile this, there's a short CMake file. It's in the tutorial itself as well. And then running this in Julia, you just have to give the path to the shared object that was generated by compiling the C++ code. And then when we load this shared object using the wrap modules function, which comes from the CxxWrap.Julia package, it will create the Julia module and the functions that are inside it. So after that, we can just call in the hello module the hello function, and it works as expected, whether it's the lambda or the regular function. So behind the scenes, I'll, given the time, not go into this too deeply, but obviously the macro, it generates a C function that is at some point called using ccall from Julia. There are some other entry points in the library as well. But so to build the method itself, the method function is declared like this. So it's very good that we have variadic templates for this kind of work in C++. Otherwise, it would be very painful to account for all possible number of function arguments. And we then, with this method function, we create an object that is later on passed to Julia. So it contains all the argument types and so on, and the pointers to use. So we can have a basic function pointer, which is the pointer to the C function, but the function may not be callable as a C function. For example, if you have a lambda, you need to wrap it up in a standard function, and then it will have an extra argument, which is the tongue here, which is actually a pointer to a standard function from C++. So this is basically I'll skip over this because otherwise I will run out of time. So this is basically the C function that gets put here in the function pointer, which can take then the functor, which is cast back to a standard function. So why are we doing all this? The main difference with Python when you want to write an interfacing library is that it is very difficult using the Julia C runtime and its public C interface. It is very difficult to define a method directly in C code. So what I have to do, or the easiest thing to do, is to pass the required data structure to Julia and then use Julia metaprogramming to build the functions themselves on the Julia side. So that's basically how it works for functions. So I will show you how efficient this is now. Basically, we have a function that loops over all the elements in an array and then multiplies every element by 0.5 and stores the result in another array. So that's intentionally very simple, and we will benchmark how long it takes by calling in the inner loop the function in different ways. So we call a regular function, a regular Julia function here. We call a regular C function using ccall, a regular C++ function using CxxWrap and a lambda and so on. And for reference, we did the same loop purely in C++, so where we have the for loop implemented in C++. And so then the resulting timings are this. So we see that Julia and C++, as promised by the onset in Julia, they are at the same level, which is logical in this case because it calls LLVM in the background. Here on my Mac, it calls Clang for the C++ code, so there's probably the same machine code behind these two functions. If we replace the half function by calling into a C library directly, we see that there is some overhead appearing, but it's not dramatic. And it's the same if we use CxxWrap with a regular C function. So a regular function, with that I mean that it has argument types that can be passed directly to Julia, and that there's no fancy things like a lambda or anything, so there is no standard function necessary to wrap the object that we are calling. If we have a lambda, then we have the standard function overhead which gets added. And then another interesting case is if we implement the loop in C++, but from C++ call in the inner loop Julia function. So you can get to a compiled Julia function, you can get a pointer to this function and call it as a C function. And then we see that also in that case, the overhead gets slightly higher, but it's still for functions that do something more complicated than just multiplying two numbers. The overhead of calling a Julia function from C++ is perfectly acceptable. Then to expose the types, again the syntax is quite similar to what we have in Boost Python. So we can, here we define just a small toy class. We have the add type function, which takes as a template parameter the C++ type and as a string the type name that you should have in Julia. You can then, if you don't immediately close this statement, you can add dots to add all the methods that you want to wrap. So here we just add get a, and we say that it has a constructor taking an integer as an argument. So then on Julia, doing the same thing as before, we can create this function or this type here and call a function on it, and it returns the expected results because we passed the 42 to the constructor here. Note the a allocated here, so that's the type that we have created, and the void pointer, which is a pointer to the C++ object itself. So why is it a allocated and not just a? So in fact, wrapping a type creates three different types. One abstract type that is named, the name that was actually given, and then a reference type and an allocated type. The difference has to do with memory management. So if you have called a constructor, internally it will have allocated the object on the heap with new. So it would be good if someone at some point called also the delete function, and so that's why we have the allocated type, which is a mutable struct which can have in Julia a finalizer associated to it, and so if the object goes out of scope and the garbage collector gets called on it, or you finalize it manually, the destructor gets called and we don't have any memory leaks. On the other hand, let's say you have a function in C++ managed memory that returns a reference to an a, then it will return the constant type a ref, which is not garbage collected, or which will not call the destructor internally, which is also good to avoid very nasty crashes of the program. It's also an additional benefit that the A type itself is abstract, because in C++ we do have concrete inheritance. So this means that every wrapped C++ type can inherit from another wrapped C++ type, because they are all abstract as far as Julia is concerned. So now I have a lot of slides about the more complicated cases involving inheritance and templates, but I propose to skip over those to give enough time to Keno for the Cxx.jl. So maybe we can come back to this if there happens to be enough time at the end. So one more small thing I want to show is the package, the real use case I have for CxxWrap, which is wrapping Quaternions.jl. Solving a partial differential equation on a grid, here just the Laplace equation, which is gives you a solution here, a double parabola with 1 at the top. And so one performance sensitive part of this is the assembly loop, where you basically loop over all the elements and then call C++ code here. This is basically from the Quaternions tutorial, the basic example. So if you would wrap this directly in Python, for example, having a for loop calling lots of wrapped functions here would be extremely slow. In the wrapped Julia code, it looks almost the same as the C++ code, and we can see that the performance of both versions, in this case we have the matrix filling function, it's also on the same level. So here I selected the benchmark that was faster for Julia. On another machine it was the other way around, but I conclude that they are at the same, more or less the same performance level. There would be no real reason why Julia would be faster than C++ in this case, but it's on the same level, let's say. So I think it's time to pass over to Keno.
Yeah, sure. Are there any general Julia questions I can answer?
Was it named after someone's girlfriend?
No, it was not. Unfortunately, the naming story is very boring. Somebody just suggested it outside the co-developers, and it was thought to be a good name, and it stuck. We've made up various stories, so I can, tell you one of them over drinks later. A good thing to say is that it's named after the mathematician Gaston Julia of the Julia set. So that's a good one. It's not true, but it's a good story.
Did you look at other multiple dispatch systems like CLOS, Dylan, Closure?
Yeah, so we're broadly aware of them. There's some design differences. I personally wasn't involved in the early design of the system. I joined about 2 years after the first code was written, at which point sort of the basic design decisions were already decided, so I can't say exactly which parts were chosen because they were that way in another system.
For example, does the argument order can influence the resolution, for example, in presence of ambiguities?
So you get for ambiguities, you get an error, is the current design. We have talked before about resolving ambiguities in favor of the first argument, but that didn't really seem too popular.
I think it's a horrible idea.
Yeah.
Are those ambiguities, can those be hidden behind a namespace, like a module or scope?
Yeah. So there's people disagree on whether it does what they want, but basically no namespace in Julia is privileged. The only sense in which a namespace is privileged is that the prompt is attached to a specific namespace, which uses a specific standard library. So, if you use that one, then people complain, oh, the standard library is privileged, but you could attach the prompt to a different standard library, and that's in fact a useful technique sometimes when you're working on the compiler. You can spin up a prompt attached to the new copy of the compiler, so you can test compiler changes while still sort of maintaining the interactivity being compiled by the old compiler if it's not quite stable yet. So.
Kind of goes to my other question about introspection. Can you remotely introspect? Is that kind of
remotely as in out of process, or?
From a different computer maybe?
So there is distributed computing facilities that have been there for a very long time, which you can basically do arbitrary remote procedure calls, including introspection. Out of process introspection is interesting. I have something that does it, but it's not particularly stable yet, and it's something we're working on. But in theory, it's possible, and there's various fancy things you can do, but it's not something that the average user would do at the moment. Okay, I think we're good on the recording. So, hi again, everyone. Just to reiterate, since I know a couple of people walked in late, my name is Keno Fischer. I work at Julia Computing, which is a company that we founded to advance the development of Julia. All the co-developers of the Julia, the original creators, are amongst my co-founders. And what I'm going to be talking to you about is my package, Cxx.jl, which is a standard Julia package. You can get it as you can any Julia package, which just typing pkg.add Cxx if you have Julia installed locally. As of right now, this may or may not work. It has a significant binary dependency because it ships a C++ compiler, which is always a bit of a nightmare to get working on arbitrary user systems. We have a solution to this in the next version of Julia where we streamline all of this, which it should just work. I had hoped it would be done by now, but as software is always, the release is late. So in a month or two, I can guarantee you this will work right now. It'll work if you have like a standard Linux system or an OS X system, and anything more exotic, you might run into weird compiler errors. Okay. But what Cxx is, it's basically the opposite approach to Bart's CxxWrap package. So in CxxWrap, you define all the glue code in C++. So you have a C++ file that declares, okay, these are the functions I want to expose to Julia, and then it uses the Julia C API to create the runtime data structures that to the Julia runtime system
specify what functions and types are available. Cxx takes the opposite approach. So Cxx, rather than using the Julia interface to create Julia types, it loads a copy of Clang in memory and uses Clang to parse C++ code and generate C++ in memory. Now, in order to do this in a dynamic language, you sort of have to have a dynamic version of C++. And if you have that already, what you can immediately get is basically a C++ REPL, which Cxx provides and is one of the most popular features of the library, actually. So the Julia REPL has this notion of REPL modes, where if you hit semicolon, you get a shell. If you hit question mark, you get help. And you can plug into this. So when after loading the Cxx package, if you hit the less than key, you get a Cxx REPL, and this behaves basically as you would expect. And if I make typos, let me know.
Inlining C++ code and your Julia code, is that basically the idea?
Yeah. So the idea is basically, in CxxWrap.jl, you write a bunch of glue code in C++, and then it exposes that to Julia. The fundamental idea with Cxx is that you can mix and match Julia and C++ sort of very naturally within the same program. Because I really hate glue code, whether manually written or generated, because there's just all sorts of problems with it. So, I'm a compiler person, so I said, okay, I have a compiler, I can fix this. So I can write Julia and C++ in the same program. And you can access variables back and forth. So let's say I defined a variable like globe, it's world. Julia has Unicode variable names. Then I could do things like that, right? So what happened here, right? I had a variable in Julia called Unicode globe, and then the $sign in front of it means interpolation, and it's a sort of generic interpolation syntax in Julia. It's used for string interpolation and command interpolation. One thing to point out, though, is that this interpolation is not string interpolation, it's semantic interpolation. So, it didn't somehow print out world to a string and then splice that string in there and then parse that. It, parsed, basically, think of SQL prepared statements, right? And said, okay, something else goes here, and then it did it at the actual type level. This works the other way around in the REPL by having special assignment syntax. So if I say, a std string C++, and then I look at A. Sorry for the compile time delay. It's currently compiling C++ introspection code. But so one, this is sort of the default printing of this. And if I, for std string, there's standard conversions defined to the equivalent Julia type. But what I wanted to point out with this is that C++ values retain their C++ character in the Julia program. So basically, what Cxx does is it reflects some approximation of the C++ type hierarchy into Julia and retains C++ values as C++ values for the primary reason that this way you can put them back into C++ and have the round trip not affect what you get. So this is the printing is horrible, and you can define printing. But what I wanted to show with this example is that things retain their C++ characteristic in Julia. Okay, so let's do a couple more fun examples of this kind, and then I'm gonna semicolons. What did I do? I'm not quite sure. Okay, well, let's skip this. Okay, so the previous example didn't work, but I don't know why. I'll have to debug it. But what this does, so the colon in front of the parentheses in Julia quotes an expression. So rather than interpolating a value, this interpolated an expression. So every time it hits this line in the C++ code, it will actually go and so it will go and call that function, or rather what it did is it asked the Julia compiler to generate code corresponding to generating a random integer. You can nest this, which I'm not going to show because nesting it takes too much space on the screen, but basically you can call back into C++ from inside the callback and then call back into Julia and pass functions back and forth, and it gets complicated very fast. And it's oftentimes not useful, but sometimes it is when you have like a loop in one or the other language and you want to use a variable defined in the auto scope. Okay. So now I'm going to switch gears slightly and work with a C++ Quaternions file that I found on the internet. I'm not going to go through it, but it looks like standard C++. It's a templated class that does computations on quaternions, right? So right, so I can define a quaternion in C++, and using the special syntax that we defined that we saw earlier, I can assign it to a Julia variable. And in this case, the standard printing is slightly more useful than this for std string. And you can see, okay, A is of class quaternion double with X, Y, and Z members. So now what I'm going to do is I'm going to define addition and multiplication, and I'm going to tell Julia, okay, anything that is a C++ value, because remember values retain the C++ characteristic, in order to add those values on the Julia side, go back to C++, and I apologize that this wraps over the line, but Icsx basically says inline C++, which basically just means that it's at function scope rather than at global scope. And you may be able to see it or may not, but the idea is basically, okay, Julia, whenever you want to add two values that came from C++, put them back into C++ and do static overload resolution in C++. This works as you would expect. Assuming the C++ library is correct, I didn't actually check, but it did something. So, good enough for the example, right? One aspect of Julia, since everything is generic, we defined plus and we defined multiply, but we can also carry it in Julia's exponentiation. So a squared is defined automatically on a, even though a is a C++ value that Julia doesn't know anything about other than that it knows how to multiply it, right? So that's sort of one of the. I want to pause here a little bit because this right here is something that actually makes Julia extremely powerful, because Julia takes generic programming and dials it up to 11. Because even though the Julia standard library that defines exponentiation doesn't know anything about C++, and C++ doesn't know, or the C++ library doesn't know about anything about exponentiation, because of the way that dynamic multiple dispatch works, these work together no problem. And I want to expand on that just slightly more. So I'm going to define a couple more methods and just show how I want to work with this. Because the primary reason that I initially developed Cxx.jl when I was in college was because I wanted to interactively explore C++ libraries that I didn't know. So when I get to a new C++ library, they're often huge APIs that are terrifying, and things don't compile and everything is horrible. But I found it actually very nice to just sort of start at the REPL and build interactively in sort of this kind of interactive setting. So that's what this is for, and you might see some of the remnants of that. But I want to show a little bit of what I would do with things like that. So this is the default printing, but we might want we might want slightly more compact printing for it to fit on a line. So I can tell Julia, okay, when you encounter something, and there's another macro called Cxxt, which is C++ but in type context. When you encounter a Quaternion class templated on a Julia type parameter $t, so this where t syntax is how you do basically template type name t explicitly in Julia, and I'm going to talk about that slightly more in just a second. But you can template C++ types on Julia types, including type parameters, and this basically just tells Julia, okay, when you want to display any C++ Quaternion type, what you do is you print out all the full components with the relevant basis elements and all of that. So I promised I'd talk a little bit more about the syntax up here. So this is actually first-class syntax. So you can define basically a type alias. You can basically define a type alias that by explicitly introducing one of these type variables and parameterize a C++ type over it. And this is useful for things like standard vector, right? If you wrap a C++ library that has a standard vector of something, and you want to say, okay, I can do the norm of a standard vector of this type more efficiently, right? You can. It basically allows you to integrate C++ values directly into Julia. And another thing we can do is actually define a Julia site constructor for this C++ type. And I apologize about the syntax. This is the last version of Julia, which was in the middle of transitioning the syntax, so it'll look nicer in the next version. Basically, what this would allow you to do is, write a Julia constructor. This table is very wobbly. Write a Julia constructor and get a C++ object back, and just to make the point, I didn't actually define. I added the object directly to the Julia representation of the C++ object. So if I now did something like let's say long on 1, 2, 3, 4, that also works, as does interpolating a Julia type as the type parameter, and all kinds of cool stuff, right? You get the point. Basically, the point is integrate Julia and C++, in whatever way, do whatever autoconversion is possible. Just get out of my way and let me play with C++ interactively. So that's Quaternions. We can do something interesting. This looked better on a smaller screen. Let me zoom out slightly since the details aren't important. So this is in Julia what we call a comprehension, which is basically just a compact syntax to generate an array by iterating over some Cartesian iteration space. So I just defined here, a 10 by 10 array of different quaternions, and it doesn't have to be a matrix. If you wanted to, if you wanted to do multilinear quaternion algebra, which why not? You could. Oops, that was too much. But so Julia has very good support for multilinear algebra, and since everything in Julia is generic, you can also do multilinear algebra over C++ objects if you were so inclined. But for screen space efficiency, I'm gonna use the matrix, and just to drive the point home that I made earlier about generic programming, matrix addition works fine. Matrix multiplication does not, and it will tell you why. For matrix multiplication, it would like to know what the 0 element is, so we can just tell it that, by just defining it in the same way, to get a 0 element of Cxx quaternion of parameter type t, just call the constructor we defined earlier with the 0 element for that type, so we can do computations in the type domain, which is useful for things like this, for writing generic code, and say, okay, just give me that 4 times and splat it in. So if we do that, matrix multiplication of arrays of these C++ values works automatically, right? Matrix multiplication is more complicated than just addition. Addition just adds everything, but matrix multiplication has has to do more complicated things, and Julia has various support for linear algebra over abstract data types as long as they define plus minus division. So a little bit showing off Julia's generic programming capabilities with the example of it being a C++ value, but I hope you get some idea of why we think some of this stuff is cool. So I have a couple more minutes, and what I would like to do is tell you how it works, in sort of rough terms at least, because there was some questions about that, and some of that might be technical, very technical, so I apologize if I lose some people. But basically, the way that the Julia compiler works is, we parse code, and then we have some lowering, then we do what we call type inference, which is basically devirtualization, and then we go to LLVM, and then we go to assembly. And
lowering, is that expanding in macros?
Yeah, so yes and no. So lowering is basically goes from an AST to a linear IR representation. I'm gonna get to macros. That I was gonna add some extra arrows. So this is sort of the standard Julia compiler pipeline. It's very simple. One sort of oddity about Julia is that arbitrary amounts of time can pass between any of these, because you can parse first, treat that as a first-class data structure, and then send it off to lowering later. But one thing that makes Julia very powerful is that you can hook into this process at any level. So if you wanted to hook in at parsing, that'd be macros right here, which can do syntactic rewrites. If you wanted to hook in after lowering, or not after lowering, but sort of during the early parts of inference, there's something we call generated functions. And if you wanted to hook in at the LLVM level, there's something we call, or there's basically inline assembly for LLVM, which we call LLVM call. And Cxx.jl uses all of these to make the illusion work. So at the at the very top, there's all of these various macros that you've seen me use throughout the entire talk. So in Julia, whenever I, let me make this slightly bigger again and actually go back to the top of the screen. In Julia, whenever I prefix a string literal with a name, that's actually a string macro. In Lisp you might call it a reader macro, but in Julia it has to be delimited by string literals because that makes arbitrary reader macros just make all kinds of tooling horrible. But so this is oops, didn't mean to hit enter that early. But so this is a macro. So this hooks in at the macro stage, and it gets the raw text, and it turns it into something. So the Icsx debug macro is something that we haven't seen yet, but it's sort of a debugging and introspection macro that I add, and it basically shows you, given something that you would put in an Icsx macro, what's the Clang AST that it actually generated under the hood. And if you again, I apologize for all of the word salad on the screen, but the main point is basically that what it did was we can even see it here. So one thing, since I didn't make any typos, we didn't see any errors, but you get Clang, C++ syntax errors. In this case, I forgot a semicolon. So basically, what it gave to Clang to parse was basically Julia var1 plus Julia var2. And then Clang gave us this and wrapped it in and told Clang, okay, parse this as a function decal, and then says Clang, and Clang said, okay, no problem. This is a function decal with Julia var1 and Julia var2, both of which are quaternion double, and then we went through the standard standard C++ thing. So that's the macro. So let me pull in the debugger to actually step into some of the guts of this. So let's say let's do this exact function. So okay, so this is just a simple function, and we can step into it with the we can step through it in the, actually let me show off what we're going to step through first. So at code lowered, if you look back at our handy little chart here, at code lowered shows you what the code looks like after lowering. So all the macros have been expanded. So if we say add code lowered, what does the code look like with the macro expanded? Well, it says, okay, call a function in the C++ library, which is an implementation function. There's a reference to a compiler. You can have multiple instances of Clang. Say, one has RTTI, one doesn't have RTTI, one is actually an Objective-C compiler. All kinds of things that people actually want. It has a reference to the compiler. And then it says, okay, we're going to operate on buffer 59, which the macro generated, and then it passes the values. So basically anything that you wrote here in the interpolation, it would paste as a Julia AST in this case. So this, at this point, is a purely syntactic rewrite. So it doesn't know anything about types. So no C++ parsing or expansion has been done yet, because in order for C++ to do overload resolution, it needs to know what the actual types are. So that is not available at this stage. In this diagram, inference is the thing that deals with types. So this is purely a syntactic rewrite, and it's a complicated syntactic rewrite, but it's a syntactic rewrite nonetheless. Okay, so let's go back to the debugger. And we can step through all the calls that we just saw in lowering until we get to this one. So Cxx.jl is what I called a generated function in this diagram, which means that it's basically a compiler callback. So when this function gets called, Julia will, if it doesn't have a cached value, call back into the compiler and ask it to generate code for it. So since the generating code part of this is more complicated, the first thing I'm going to do is just step into the function as if it were a regular function. So ignore the fact that it's a generated function. And I apologize for the debugger. Since it's a generated function, it doesn't have source info, so it just shows the first line of the compiler. But if we step through it, you see a bunch of calls, and eventually, we end up at an LLVM call. So what this generated function did is it analyzed what we parsed in and told Clang, generate me some LLVM. And then at this point, we're feeding the LLVM back in to our standard compiler pipeline through the LLVM call intrinsic. So we can look at that in some more detail by using Cxx.jl, and you'll see why I wrote Cxx in this very example. So there's a file LLVM includes. It just has a bunch of hash includes for various LLVM headers that I like. But what we can do is we can so this pointer that it passes to LLVM call is an LLVM function pointer. Oops. And this is, again, using Cxx.jl. PCPP is just a convenience macro for pointer to this type. Right, so we went into C++ mode and said, okay, C++, please call the LLVM dump function. So you can call C++ code in dynamic libraries. LLVM is already loaded because Julia uses it. If it weren't loaded, you could DL open it, just as usual. But so this is basically the LLVM function, the LLVM IR that Clang generated, and it's very simple. It basically just has 3 pointers to Julia. Julia uses LLVM types, but Cxx doesn't retain them. It just says they're I8 double star. But basically, what Clang emitted was that, which is very simple LLVM IR, with eventually just a call to this function declaration that it defined earlier with the 2 parm decals that we saw. And this is standard C++. LLVM will go nuts on this, right? And then it does inlining and all the standard things that LLVM does. So this can generate quite efficient code, sort of zero overhead, and even inter-language inlining between levels of C and C++ if you all run it on the same LLVM execution engine. So that's that. But let's quickly go back to this, and where was I? Yeah, there. Oops, now I want it. So there's a command in the debugger SG which will step into the generated function, and again, the generated function is basically a compiler plugin. So we're in the generated function now, and don't have too much time to actually step through all of it, but just to give you a rough idea, it had this buffer 59 reference that the macro created, and then looks that up to say, okay, what's the buffer that reference value 59 refer to? What's the file name? In this case, none, because we did it at the REPL. But if you did it in a file, you would get actual source locations, which is nice for errors and debugging. And then the next thing it does is generate this generate this function decal that we saw earlier that I printed out, and we can see it again. We can see it again here, right? The function decal. So and the important point is, at this point, we're in the generated function. And what the generated function gets as arguments is the types of the values that it was called with. So at this point, the 59 was part of the type. And it also knows at this point what the types of the two A's are that we passed in as arguments. So it knew that they were both, quaternions of double. So at this point, we generated a Clang level function declaration that was specific to adding two doubles, quaternions of doubles, which allowed Clang to do the standard, static overload resolution. So we did that. Then we told Clang, hey, go ahead and generate some LLVM code for this. Here's some extra code which has to do with various nested callbacks, where it needs to generate templated lambdas basically to do callbacks. Complicated topic, let's skip over it. And then it's very simple. It just says Clang, hey, that function declaration that you just declared, give me a reference for it, and then generate a call to this reference. And there's some trickery buried in here which basically fixes up what Clang's notion of the parameter is at the LLVM level, so which connects the Julia declaration to the C++ declaration. Basically says, okay, for this parameter, rather than using the first argument of this LLVM function that you generate, use the first argument but bitcast it to whatever pointer type you were expecting. There's lots of details here, but that's basically the high level. Tell Clang to generate a function declaration, tell Clang to call it with our arguments, and some trickery for move constructors and various other things that I'm not showing, but that's basically the idea. And then we're back. So this was, since we did the SG, it stepped through the compiler. Now we're back to where we were before, where if we step in, we'll get to the LLVM call that the compiler just generated. Okay, and the timer tells me that I went 3 minutes over from what I was supposed to. But yeah, are there any questions about this? I know some of this was very fast and lots of text, but yes?
Can you suck in a non-header-only set of C++ files to use?
So, I mean, I showed an LLVM example. So there it used LLVM in the dynamic library. You can, it has a complete C++ compiler, so you can compile arbitrary C++ code. You don't really want to, because this has all of the compile time disadvantages of C++, but at runtime. So, if you can run into problems, and I plan for the future to do precompiled modules to help with that. But it's a full C++ compiler, so anything a C++ compiler can do, you can do here. So does that answer the question? Was there something specific you were looking for?
Yeah, I guess I was just thinking.
Oh, for the recording, the question was, can you do non-header only C++ libraries? So,
I think it answers my question. I was just going back to sort of the beginning,
yeah.
where you just switched over to C++ mode and did include
Yeah.
the quaternions, and then you just had the whole
Yeah.
class. If I wanted to do something like that very quickly, but for a class that had an accompanying source file.
Yeah, so you could hash include the .cpp file, which would work. You could compile this CPP file to a dynamic library and DL open it. And as long as the header file is accurate, that'll work. I think those are basically your options.
Can you read in a whole directory of like C++ code and then?
So in theory, yes. I haven't explored too much in that direction. To be honest, this is basically as much as it could do 3 years ago, and in the meantime, I've been working mostly on Julia itself. But yeah, there's lots of those kinds of, and automatic detection of these kinds of things sort of correspond. Like Julia has very extensive libraries for colors and images. So if you're working with say OpenCV, which is one of the libraries wrapped with this, you could automatically introduce various conversion methods and all of those kinds of automatic stuff. But I don't have any of that right now.
Does Julia have exceptions, and do the C++ exceptions?
Yes.
Map?
Yes, actually. That was actually really complicated to figure out. So it worked at one point. Let me see if it still works. Yes, it worked. Okay. So the red error thing is Julia printed it, and it. So if you throw in Julia, it prints the red error thing, and then the hello. And C++ thing, it does the same thing, but at the Julia to C++ boundary, there's a custom personality function which translates from one exception domain into the other one and rewraps it as a Julia exception. So yes, it works.
How are Julia exceptions implemented? Are they like an either monad, or are they based?
No, so Julia exceptions right now, set jump, long jump based exceptions. We are planning to do better in future versions of the language, probably using an either monad for sort of explicitly annotated exceptions. So if you have an exception that you expect to occur during regular control flow, like a network exception that you can handle and do a retry or whatever, as opposed to terminating exceptions which the world doesn't exist anymore, right? Like those kinds of exceptions that you would still want to catch in an interactive environment, in case you can recreate the world somehow, but you wouldn't want to handle in regular control flow, and pessimize abort the world more by using dwarf-based unwinding, for example, and less pessimization for the common case where you expect to actually handle the exception in user code.
We're also working on that, and it might be a good idea to
Sure.
Communicate. I'm not an expert. I just
Yeah.
see a lot of experts talking about this.
A few words about memory management in Julia.
Sorry?
Can you describe
memory management? Yeah. Julia is a GC language. So we standard mark sweep, concurrent garbage collector. Did you mean just in general or specifically with the C++ integration?
No, just in general.
Yeah. So.
Well, but it leads to maybe some problems when interfacing with C++. You have to.
Yeah, it leads to problems. So let me address the general memory management question first. So Julia in general is garbage collected with automatic memory management. For performance, we often try to elide allocations even if they are semantically there. So we can do various heap to stack promotions, which is necessary for performance, and we can do various other tricks. But fundamentally, it is a garbage collected language with that. With respect to C++, this causes various problems. In Cxx, I introspect the destructor and see if it's interesting. If it's interesting, then it's slower, because then it needs to use the finalizer mechanism in Julia to call the destructor when to call the destructor when the object goes out of scope. It can also be annoying for interfacing with C++ libraries that expect scope-based resource acquisitionist initialization. If libraries use that pattern, it can be sometimes hard to use them from Julia sort of in the naive way. So if the way to do that usually is then to just use a block of C++ with explicit scopes, because in Julia, if a library uses that pattern, the destructor will only get called when it goes out of scope for GC purposes, which might not be until some while afterwards. So C++ libraries can expect that to happen at the end of the scope, which in Julia it wouldn't. And I'm out of time, but I'm going to be around the rest of today and tomorrow morning. After that, I unfortunately have to go back and finish the release of this language, which is my actual job. But if there's, I would be perfectly happy to take more questions, and I'm sure there's questions for Bart as well. And I apologize for taking up all of the QA time if anybody had questions of that nature. All right, thank you very much.